examples, and then we'll take new topic. We call this alternating series. After the half of this lecture, inshallah, we'll start finding the roots. Okay, the unit number 2, finding the roots, how we find the roots of linear or nonlinear equations. Okay, so in the previous lecture, ya shabab, we introduce or we take a review to Taylor series expansion, and we said Taylor series is one method that's help us to approximate the smooth or the continuous function, to approximate it in forms of a polynomial. So why we do this one? Usually we want to simplify or to put the function in an approximated way that will help us usually to program it. Because sometimes if we have functions with integrations, for example, or in terms of logarithms or sine, cosine, sometimes this is difficult to do or to implement this using our codes, for example, programming in MATLAB or programming in Python. Or if we program this one, usually our algorithms will be so heavy. Okay, we give you some examples at the beginning of this lecture. Sometimes I tried this by myself. I ran my algorithms, for example, for control algorithms. Sometimes takes 3 days, 4 days, sometimes 5 hours, 3 hours. Okay, some later, for example, after we use these numerical methods, that will help us to implement or to get the results, for example, as soon as possible. This also to help us for consume our time to get a good result or accurate result by using these methods. Okay. Yes. Okay. So what's Taylor series? This will be the standard form Taylor series. I will give you this in the exam. You should know. By the way, Shabab, we have a quiz. Okay, Wednesday, inshallah. Taylor series. Okay, you have one problem, Taylor series, to solve. Inshallah, I will send you announcement. You have this Wednesday. At the beginning of the class, you will have one quiz, 10 minutes or 15 minutes to solve one problem, first quiz on Taylor series. Here, for example, this Taylor series, we want to protect the value of xi plus 1 started. This we call the start point or center point or the base point. We start from xi. So in this case, we want to evaluate this function using this form. So we have here, this is the evaluation of the function at the center point. We need also to compute the first derivative. So in this case, to use Taylor series, we need to have the derivative. Also, the derivative should be available for the function. Okay, so if we have, for example, constant, so the derivative will not be available here. So, for example, if the function equal, for example, 3000, if we take the first derivative, this will be 0. So we have here just one term. Okay, and the rest also will be zeros. This term, often we call this the step size. Also, you should recognize that the step size equal xi plus 1 minus xi. So for simple version of Taylor series, we use Maclaurin series, which will be a special case of Taylor series. We use it with center xi equals 0. Also, we reviewed truncation errors, and we said this is errors usually because of mathematical computation or approximation and the mathematical procedure. So, for example, if we have exponential function, exponential of x here, or e of x equal 1 plus x squared over 2 factorial plus x cubic over 3 factorial plus, for example, to infinity term. We have terms to infinity. So, for example, if I take only these two terms, for example, from here to here, so the rest will be, we call this the truncation errors. The rest that we have, that I omit, we call this the truncation errors. So, for example, here, if we only take 3 terms, or 3 terms are used for our approximation, so the truncation error is equal the exact solution or the true value minus our approximation. Okay, or we call this the remainder later in this lecture. Okay. Okay, so this is the approximation and this is the truncation error that we have. And also we take different examples here. For example, we take this polynomial and we said sometimes if we start from 0, here, for example, this function of order 5, sorry, of order 4. So if we take the derivative of order 5, so here we'll get zeros. So after the order 5, we can get the exact solution, but in the reverse form. And after that, also we studied the effect of nonlinearities and the step size. Okay, and the effect of nonlinearities and the step size. And we take it one example here, example 4, and we said if we have x of power m, and we change the order of x of m, for example, from 1 to 4, that means we make the system more linear. After that, we examine the system. I think we take this theoretically and we stop it after that. So here, for example, if we change the value of m from 1 to 4, so for example, m is equal 1, so here I have x power 1, and we use the first order expansion to approximate the version or the function here. And after that, we compare the errors at each, all the errors at different steps or different version of x or different value of m. So here we have the range that we started from is from 0 to 1 to 2. Okay, we want to evaluate the function from starting from 1 to, we want to protect the value at 2 or estimate the value at x equal to. So here we have this solution, for example, for m equal 1. So because here f of x is equal x only, so the true value of the function is equal to. Okay. Because here in the question for our approximation, we use only the first order. No need for the second order, third order, we use the first order. So here the first order or the function xi plus 1 is equal f of xi plus f or the first derivative xi multiplied by h. Okay, and h equal 1. And the first derivative is equal 1. So here the difference or the error or the truncation error between the true value and the estimation is equal to, and the true value is equal to. So the remainder is equal 0 or the truncation error is equal 0. So after that, we increase the value or the order. Now m equal 2. So the actual value is now will be just direct substitute instead of x by 2 and power 2. So this will be 4. Also, we use the first order approximation here of the function by using the function at the center point multiply or plus the first derivative at the center point multiplied by h, and h equal 1 here. So here I have 1 plus 2, this will be 3, and the true value is 4. So the error will be 4 minus 3 will be 1. Okay, so the truncation error equal 1. After that, we increase the value to 4, the value of m to 3, and after that to 4. We find that if we increase the value of m, so the error will increase. So here we have error 0, after that error 1, and then 4, and then 11. So if we increase it more, so we go as far from the true value. Okay, we go far from the true value. So as a result of that, so we can summary that or conclude that if we increase the order or the of the function x, for example, from 1 to 4, or we can say that if this function becomes more linear, so the error or truncation error will be will increase. Okay, the truncation error will increase. This is the first one. So if the system goes nonlinear, so the truncation error will increase, or the error in our estimation will increase. The second thing that we want also to evaluate is the effect of the step size. And we said the step size is not just h, and h just the difference between the center point and the point that we want to the point that we want to estimate the value on it. So here we use the highest order of the function. Okay, we use the highest order here, and here we have f of x equal x power 4. Okay, and the step size is 1 at the beginning, and this is x starting point is 1. So here I have the starting point is 1, and h equal 1 here. So in this case, the true value will be 16, like what we have, and first order approximation will be 5, and the error between the two, this will be 11. After that, I increase what will be, I want to study what will be the effect if I decrease the step size. So now if I decrease the step size by half, and instead I have the step size by 1, I get 0.5. That means xi plus 1 now is equal 1.5, not 2. Okay, xi plus 1 will be now 1.5, because center point plus the step size. Okay, the step size is 0.5, so here xi plus 1 will be 1.5. So if I evaluate the function at this point, I will get this one. This is the true value. Okay, this is the true value, and this is the first order, and this will be the error. So if we decrease the true values here, or the step size, you can see if we decrease the step size from 1 to 0.5 to 0.24 to here we have 0.125, like this one. If we decrease the step size, so the error will decrease by using the same function. So that means the effect of the step size, if we decrease the step size, so the error will be decreased, because we just estimate step by step. Okay, we just estimate step by step here. Any question, Ishwa? So as a summary here, يا شباب, to reduce the truncation error, here, what we do, usually we reduce the step size or increase the end derivative. That means we increase the number of the terms. I can put it in general form, increase the number of the terms. Okay. Number or terms in Tyro series. Okay, so that means increase the derivatives, or we can say increase the terms in the Tyro series approximation. Also, if we reduce the edge, or we reduce, for example, the step size, that means the error will go smaller and quicker. So we converse quicker to the stopping criteria that we want. Okay, so we have different criteria here, eitherwise by reducing the step size or by increasing the number of the terms that we use. So in this case, we can reach the exact solution. So usually, sometimes some functions, it is difficult to get what we call the derivative of these functions. So if we have large error, for example, in this case, we might enhance our estimation by reduce the step size. Any question until here? So until here, we might say this, we will finish this what we have about the Tyro series expansion, and we have another concept we call these iterating functions. Derivative of mean value theorem. It's stated there that if a function f of x and its first derivative are continuous over interval xi to xi plus 1, so this function, it is continuous over this interval from xi to xi plus 1. So here there will be exit at least one point on the function, this for example the point, that has a slope determined by the function of z, f of zeta. This slope will be parallel to the joining point between xi and xi plus 1. So this slope will be parallel to the joint point between xi and xy plus 1. So the parameter zeta that we have it here on the x-axis marks the x value where the slope is x. So this will marks the x-axis where the slope is x. So this is the derivative mean value. We need this, for example, to compute the errors, or also to compute the roots later. So alternating series, what do we mean by alternating series? Alternating series, that mean this series, when we have the terms alternated, the sign of the coefficients. So for example, it's clear here we have the sine wave is alternated functions, because here the first term comes with different sign. For example, here, for example, positive, the second term will be alternately negative, the third term will be positive, the fourth will be negative, like this one. So according to this theorem, if the magnitudes of the terms is in alternating series are converge to zero, then the errors in alternating series is no longer than the magnitude of the first omitted term. What's the first omitted term? The first omitted term is this term that we omit. Okay, so the truncation error is no longer larger than the magnitude of the first omitted term. That means it is equal. So here we have two conditions for this series. If we have this series, alternating series, if you can see, this is the series S. It's contained the coefficient A1 minus A2 plus A3 minus A4 plus 2 infinity. So here the coefficient A1 should be greater than, because the magnitude of the terms otherwise should be the same or less than, reduced. Here we have, for example, A1 is greater than or equal A2. And also A2 is greater than or equal A3. So this is the first condition. The second condition, if we take limitation for the function or the general form of this function, n goes to infinity, so this will equal 0. So for this function, we can say this function, it can be converged, and we have here the absolute error between the exact solution and the estimation is equal or less than, or the error here equal or less than the first omitted term. If we take these terms, for example, to an, so the first omit, if my approximation is until here, this is my approximation. So the first omitted term will be an plus 1. So that means the truncation error here is equal the exact solution or the exact function S minus the estimation is no longer or larger than the first omitted term. This is the first omitted term we have, or the remainder that we have. Okay, this is the remainder that we have. We call this the first omitted term. So let's take an example here. After this example, we finish this unit, inshallah. If you look for this example, I want to find or compute the function, this one, or to check this function, if this function is converged. What we do here, this is the function sine 1. By using Taylor series, we will get this solution. Now the function is clear for us. This function is interlating series because we have the function now. One, for example, a positive, second term negative, positive, and negative. But if you want to check the function, this function is converge or not, we have to do two conditions, or to check the previous two conditions. These two conditions should be valid. So this one, we should guarantee that A1 should be greater than or equal A2. And the magnitude here is clear. This is 1, and this is 1 over 6. So L1 is greater than 1 over 6. So this is greater than. So the factorial now, if the value of the factorial is increased, that means the magnitude of the denominator will increase. So the value of the fraction here will decrease of this term. So as we go like this one, these terms will go smaller. So this is the first condition. We can see it is clear now. As we go, the value of the coefficient will decrease. Let's do this one. So the general formula of this one, if this is, or of this series, if I have this series, I can get this general formula of this series. This series, or S, it is equal sum, for example. Okay, from n equal 1, for example, to infinity, I have 1 over 2n minus 1 whole factorial. Okay, so for the first term, I have n equal 1, so I have 2 minus 1, this will be 1. So I have 1 over 1 factorial, so this will be 1. Second term, I have 1 over 2 multiplied by n, and n equal 2, 2 multiplied by 2, but this will be 4, minus 1, this will be 3. So I have 1 over factorial 3. Okay, so this is the general form of this series. I have summation from n equal 1 to infinity, 1 over 2n minus 1 factorial. So if we take limitation to check this condition, if I substitute instead of n by infinity, so 2 multiplied by infinity, this becomes infinity. Infinity minus 1, this becomes infinity as well. So we know that 1 over infinity, I have factorial infinity, or 1 over infinity, this equal what يا شباب؟ 0. Okay, I have 1 over infinity, this becomes 0. So this is the first condition we evaluate. I can also adjust this one, or this function, to compute the first omitted term. If I want to get the first omitted term. So the first omitted term is not n, just I have this function like this one, and instead of n, I will substitute by n plus 1. So this will be minus all factorial. And instead of n, this will be n plus 1. So after that, what I will have, so I will have 1 over 2n, multiply 2 by n, so I have 2n, and 2 multiplied by 2, this will be 2 minus 1, will be plus 1. If I compare the denominator here, 2n plus 1, with this denominator, 2n minus 1. So if the value here, 2n plus 1, is greater than 2n minus 1. But this value now comes at the denominator. So that means the value of an is greater than the value of an plus 1. This will be the second condition now is valid. So the two conditions now are valid. So in this case, the series is converged because I have the two conditions are valid now. So we want to get the general form of this alternating series. After that, we apply the limitation. N goes to infinity to n minus 1 factorial, and the power or the value at numerator equal 1. We substitute direct substitute in n equal infinity or n goes to infinity. So in this case, we have to have this value equal 0. After that, we compare this with the first omitted term, and the first omitted term, as we said, this is an plus 1. Okay, so if the two conditions are valid now, so we can say the series is converged. Any question here, يا شباب? So the entertaining series, it's here. We should satisfy this condition. It's strictly entertaining. That means we have the coefficient entertaining from different sign, positive, negative, like this one. Each term comes in smaller in magnitude than the term before it. Okay, so each term is smaller in magnitude than the term before it. The terms approach to 0 as limit. If we take limitation, so the terms goes to 0. So in this case, we can say this series converge. And if one of the conditions not valid, so the series will not converge. Any question? This is the last thing in this unit number 1. Do you have any question? Okay, so sorry, the second unit here, Shabab, here we'll talk about finding the roots, or where is the location of the roots of the functions. Okay, so during this topic or unit 2, we'll study different type of methods to find the roots or the solution of nonlinear equations. Usually here, يا شباب, we'll study classification of the methods, analytical solutions, graphical solutions, bracketing methods, open methods, and also we'll focus on the convergence notations. How this is converged, or the algorithms will be faster or slower, or we have different type of problems. Usually, يا شباب, for this topic, we have we'll cover different type of methods, and this usually from this comes from chapter 5. Okay, regarding the books, يا شباب, we can discuss. Any one of you may send me any WhatsApp about this one, the textbook. I will or share with you handouts. Regarding to this one, يا شباب, method that we'll study here, as we said, usually, يا شباب, what we'll study when we talk about finding the roots, we want to find the solution of the function that becomes 0. We want to find the value of r that make this function equal 0. So this will be what we call this problem called the root finding problems. So usually we try to find, for example, the R that satisfies that these problems. Otherwise, use these analytically, or for example, by using the numerical methods that we have it here. During this chapter, يا شباب, or during this topic, we will study two types of method. Bracketing method. This usually we start from two initial guess of the roots. So, for example, if I have a figure like this one, this is function like this one. So, in these bracketing methods, That means we start from initial guess. So for example, I start from this guess of the roots. Let's make it view to have a roots here. Okay. So here, for example, this equal 1. And I have here, this is x equals 6, for example. And the roots here at 3. Assume this at 3. So this type, we started from Bragton method. That means we started from 2 initial guesses. So we inform you that the root is located between 2 points or 2 initial guesses. I have here, this is 1 and 6. And we put here bracket, that means we call this Bragton method. So we bracket the solution here at the initial guess like this one, and we know the roots now it's located between these 2 points. So as a result, we'll try to reduce the interval or the distance between the 2 points until we minimize it step by step until we get this value. Okay, so we try to minimize the distance between the 2 points. So after that, we come here until we get the root. So from this name, we call this Bragton because we have 2 initial guesses, and after that we bracket this guess, and then we estimate or find the value of these roots. Sometimes we have more than 1 roots or 2 roots, multiple roots, depending on the function. Okay, so the name comes from this one. The other type of the function, we call this open, okay, or open method. And this open method, usually we don't have a Bragton, or we start from 2 initial guess. We have only 1 initial guess, or sometimes 2, but not Bragton. Okay, so we have 1 guess first. So any n-order polynomial has exact n roots. Okay, if any n-order polynomial has exactly n roots or n zeros, and any n or any order polynomial has at least 1 0 roots, we know this one. So in this, ya shabab, at the beginning, when we study the Bragton methods, we'll start with these 2 methods here. Just these 2 methods, inshallah, we'll cover during this chapter. The graphical method and bisection method. Okay, so the graphical method, usually we do this using our computers. If I want, for example, to find f of x or cosine, for example, x, for example, equal, for example, 7 or 17. Find the roots of this function. If I give you this function and the question to find the roots of this function. Usually what we do, we equalize these to 0, for example, minus 70, this equals 0. After that, in the graphical method, we try to plot this function. So the graphical method is one of the easiest methods that we use it. And usually we do this using softwares or computers. So just I will draw this function or I plot this function. For example, I got function like this. After that, by looking by the intersection between the graph, the function that I have, and the x-axis, I have here intersection or cross. If the function cross the x-axis, these points now, it indicates that I have different roots at this point. For example, I have roots at this point, but what's the exact value? I want to get it with minimum error, and also this also corresponds here, it indicates that I have a roots here. Look, it's at this point. So graphical method, as we said, usually we do it otherwise by using computers, Okay, we have computers or any logarithm that we can run it to draw a function. After that, we look for this figure to identify or authenticate the cross point between the function and x-axis. And these crosses, it is the not just the location of these routes. But usually, يا شباب, with this method, it's help us a lot to understand the behavior of the functions. But if we want to get the exact solution, usually we have a problem with that, with this one. Let's take this example, or we talk about this one. This the second method, bisection method. Bisection method usually it's more or convariance more than this one. And if I compare this with the graphical, will be more accurate than the graphical one. And this method also we started from two guesses. Initial guess. If I have two initial guess, if I said I started, if the question find the roots of this equation or this polynomial, if the roots located between 1 and 6. So here what we have, we just start from these 2 points, okay, and after that we look for the sign change, the sign change of the function. So what do I mean that? So if I have f of 1, if I evaluate the function, this function at value or at the lower boundation or the lower limit of our practice, for example, f of 1, this, for example, give me negative value. Okay, and also evaluate the function at the upper limit, 6, this give me positive value. Usually, if we have change in sign, this will indicate that I have at least one pole or one row to locate between the 2 points, because this is comes with negative value here, and when I evaluate the function at 6, I will get positive value. So this change in sign indicates that I have the function will cross the x-axis. So in this case, I will get one rows at least. Okay, so this is the first condition to do, otherwise by looking for the function from the graphs or by using a tabular method, like for example graphical, but in terms of table, by looking for the sign change. If we have any change in sign, so this will indicate that I have at least one pole. Okay, so this bracketing method usually we start from interval that's contain the rows, and after that we proceed for our algorithm that's be used to obtain smaller intervals. So we'll try here to comes. So if we get, for example, the evaluation of our limitation, our initial guess, here is positive and here is positive. So both functions or the evaluation of both function here is positive. Like this one, this second function, this is x and this is 1 and 6. So bisection method, it's not applicable at this case, because if I get this is positive and this is positive, maybe the system has double or even number of poles or zeros, or maybe we don't have any zeros or rows. Okay, so in this case, this bisection method in this case is not applicable. After that, we will study another method that's more applicable than this method. So we'll try to go from the sample method. After that, we'll go to more advanced techniques for finding the roots. Let's go for this example, ya shabab. We have here, this is the first example from the textbook, chapter 5. Here it gives that this is equation that represent the velocity of a mass free falling, okay, and the mass m is equal 68.1 kilogram. The gravity force is equal 9.8 meter by second square, and here this is m also c, and the time is 10 seconds. And we want to find the value of c such that the velocity becomes 40 meter per second. Okay, the velocity becomes 40 meter per second. So we get this equation from this one. So to use the graphical method, as we said, like what we did before, if we have cosine x, for example, it's equal 70, we equalize this to 0. We said, for example, this is cosine x minus 70 is equal 0. So here to have equation or the problem in terms of finding 0 or find the roots, we substitute instead of b by 40 in the equation here, and instead of b by 40. After that, we equalize these to 0. And now what we want here to do is to find the value of c that's make this equation or this polynomial goes to 0. So the value of c now, it's the roots by itself. Okay, it's the roots by itself. So if we have, for example, if we run, for example, our algorithms, if you want, for example, to run our algorithms, we might have any code, for example, to do this one. By, for example, define this equation. After that, I define the coefficient that I have, the constant at the beginning, g and m, and I have t, and also I have v. And then, for example, I try to find the solution for this equation so that this will equal 0. If I plot the function now, this is the function that I do it. I will plot the function, you can see. I will see that it's clear from the graph. I have a roots that's located between 12 and 20. Because the function now will cross x-axis at this location. Okay, so here, for example, with some softwares, we might use slide in the point, and after that we get the exact solution. And sometimes even by using, for example, zooms, if I zoom the figure, I will get some errors. For example, by computing the exact solution. Here, for example, if we estimate, or the best estimate, our best estimate, for example, for the roots, we find that the root C is equal 14.75. If I substitute instead of C by 14.7.5, so I will get the solution. The solution should be 0, but still I have some error now. That means if I substitute instead of C by 14.75, the velocity now becomes 40.059. So we have this magnitude, or this value is the value of the error. Clear يا شباب؟
Yes. Clear.
Okay, so usually this يا شباب the graphical method we do it using softwares. Okay, software or by the help of the table I will show you in the coming slide. Here we implement this function and we equalize this to 0. After that we run our algorithm to plot these functions. This function, if we have any cross point between the function and x-axis, so this point represent I have a roots here. But even if I zoom this one, if we do zoom, for example, we cannot get the exact solution. Sometimes, dependent from, we have error. Sometimes, for example, I use glasses, for example, but I will get this here, for example, 14.5. Someone, for example, mashallah, get it 14.7. And by using computer, we get, for example, 14.75. Okay, so here, this method, it's represent the function. It's give us more information about how this function behave. What's the behavior or the performance of this function? But if we're talking about the error, usually we get some values of the error, okay, because this we cannot inaccurate. We can say this is inaccurate or not systematic method. So here, for example, let's look for this one. We even otherwise, for example, plotting or by using, for example, tabular, or we call this otherwise by plotted directly or by tabulize by using tabular method here. The same method by using table. How would you do this one? I will start guessing. Bracketing, for example, I started from here. If I know this is I plot the function, I have the function here. Okay, this is the function. It started, for example, bracketing at 4 and 200. This is the bracketing point that I have, or my initial guess. So now I want to substitute the values from 4 to 40 and put these values. So I substitute instead of C by these values from 4 to 20. If I get any change in sign between two terms, so this change in sign indicates that I have a ball or a zero or a root here. So here, for example, if I set C equal 4 and I substitute in this function, okay, substitute instead of C by 4. So f of C, this f of C is equal 34.1, for example. After that, step size now is 4, okay? The step size that I use it is huge, yani large. After that, 8, I will get positive value. 12, 6. And when I substitute instead of 16, I will get negative. So this change in sign here, if I have any change in sign, if I substitute instead of value of C, for example, by different value, if I get any change in sign, this indicates that I have a root between these 2 points. So if I have change in sign, I will have at least one root exit between these 2 points or foundations, lower and upper. This will guarantee if the function is continuous and smooth. If I have smooth and continuous function, not sub-interval functions or discontinuous function. Okay, so here now I determine I have the roots is between these one. But by using this graphical, it is difficult or not accurate to get the solution, but it helps us to identify the location of the solution. This method also, the graphical method, we use it or it helps us to give us the initial guess. So from this graph, I start the initial guess. Because this graph, it helped me, I will start from these guesses. This is my guesses. So this graphical method, we can say it is the base or it is help us to create the initial guess or the initial bracketing to start. Okay, so this is about the graphical method. The graphical method, as we said, just representation method that help us to represent the function by equalize this function to 0. After that, we plot this function. If we have any cross between the function itself or the path of the function and the x-axis, so this cross indicates that I have roots at this point. Okay, so or by using the table, just substitute instead of roots from the figure. Usually we start from the figure. How I start the bracketing? Usually from the graph. If I have graph, after that I will initiate my guess or the guess points. If I have the guess point here, for example, I have guess point here. This is 1 and this is 20, sorry, from 4 to 20. I will start this initial guess. After that, I will change the value of the parameter C. I will substitute and I will evaluate the function. If I get any change in sign, this will indicate that I have at least one ball exit between these 2 points. if we can see يا شباب, if we reduce the step size here, if we reduce the step size, our estimation will be more accurate. Okay, more accurate. We might have, for example, change in sign at 13 or sorry, 15, like this one here, because here I use step size is 4, but if I have it, for example, 1, I will, so for example, at 15, the change in sign will appear. We'll have change in sign at 15. So if we reduce the step size, usually we'll have more accurate estimation. Any question about this one? So here يا شباب, this is another function by using graphical method. We can say this is graphs, for example, the graphs. We don't have any change in sign. If I try to use the table or tabular method, for example, if I use tabular method here, I don't have any change in sign. So no rows here. In B, for example, this B, I have different sign. I have change, for example, if I take the value here, this is negative, and the value here, f of x will be positive. So I have change in sign. Okay, this is indicates that x at least one row. The problem here, for example, if we go to figure C, if you can see, I don't have any change in sign between this point and this point. Okay, depending on the step size that we use, we might, for example, select this positive, and we jump this short, for example, interval. So we'll get all the values are positive. So in this case, I might say that the system, we don't have, in this function, I don't have any rows. But here we can see I have the same size, same sign, but here I have two rows. Sometimes because of the interval comes small. Okay, sometimes like this one, small interval, like this one. So this small interval dependent on the step size that we use. If the step size is greater than this interval, so in this case we cannot indicate these rows. Okay, if the step size greater than the interval, this is the interval that I have. If the step size is greater than the interval, that means I will select point, my select point here, and the step size, the next step size will be here. So in this case, I will get all the values positive. So I cannot recognize I have rows here. The fourth one, D, for example, figure D, we can say we have different sign, but here instead I have 1, I have 3 rows. Okay, so we said different sign indicates at least 1 row, but we cannot recognize if we have more than 1 row. So in general, this method, it's applicable to give us initial guess of the location of the routes, initial guess for the bracketing, to bracket, for example, the initial guess of the routes, or to start from a good interval. But this method is not accurate. Okay, as we said, but it gives us a good information about the function behavior. Any question? Okay, so here, for example, as we said, if the function hits x-axis here, this will indicate we have routes here. Okay, or the change in sign. We have two techniques here to identify the routes by using this method. Otherwise, if we have change in sign in the table, or by plot the function itself, after that we look for the intersection, or the when the function will cross x-axis, and this also will determine the location of the or of the routes. This is some graphs for difficult functions, some function, or we can say we plot this function to determine the location of the balls. So here, for example, for this function, you can see we have here more than 12 balls. How many balls or zeros or rows I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, or more than 15, like this. Okay, so just I plot the function. After that, I will look for the points, how many points this function will cross the x-axis. So the number of the points, it's determine the location of these rows. Okay, so here, for example, I have 2. Here I have more than 4 rows, like this one for this function. Any question? Okay, so here we can see we have using the computer to plot this one. I will see we might have 12 points or more than, or 20 points here, for example. So this method is good, but not systemic, and we need approach that might be it can be systemic, that will help us to provide, for example, accurate measurement of the roads. The second method that we'll study is bisection method. Okay, the bisection method, it's dependent on one condition. If this condition is valid, so we will continue doing this a lot. So bisection, from its name, we start from two initial guess, lower point and upper point, lower guess and upper guess. For example, in the previous graph, we have graph like this one, and we started from 4 to 20. From this graph, we have initial guess, and this guess is from 4 to 20, and we call this practicing because we practiced this at the beginning. So this is our initial guess. Okay, this is our initial guess in bisection method. To find the rows, we start from this one. So the second method, what we do, this method applicable only if I evaluate the function. For example, I take, for example, f of 4 multiply by f of 20. This should be less than 0. So this method is applicable. So this method can be checked. This can be checked by ensure that by evaluating the function at the lower limit multiply by the function at the upper limit should be less than 0. If I have change in sign between these two guesses, so that means at least I have one root between these 2 points. So this method will help us to find at one root that we want to find. This is the first condition we should guarantee at the beginning. After that, what we do, we usually try to estimate the location of the balls by computing the midpoint. By computing the midpoint between these two intervals. So we reduce the interval by half. Each step or each alteration, we reduce the interval by half. Okay, so if I start from here, this, for example, 4, and this, for example, 20. I will compute the interval or the midpoint. So here I have 4 lower limit plus 20 upper limit. This will be 24 over 2. This will be 12. So we compute the midpoint here. So after that, we mark the following conditions. We have these 3 conditions. I multiply the lower limit, this point, to evaluate the function here. If at 4, multiply by the lower limit. For example, here I have 12. So I evaluate the function at lower limit at 4. I already computed at the beginning. Multiply by evaluating the function also at the midpoint x of r. If this is less than 0, that means if I have change in sign, so the root lies at the lower subinterval. Okay, if I get f of xi, x of l, f of xl multiplied by f of xr is negative, so that means the roots located here. If the roots now, I recognize I have change in sign at this area. So no need for this interval. No need for this interval because I know now the roots located in this interval. So just I will evaluate the function at lower limit, multiply by evaluating the function at the midpoint, and I will check it. If this is less than 0 or negative, so the roots now located in this interval. So no need more for this interval. So now I will reduce the interval to this one. The second step, I will reduce the interval by half, 4 and 12. That means I will replace the upper limit by xi, by the midpoint. So here I will set the upper limit equal to the set point. So no need for this one. Again, I will compute the midpoint now. So I have 12 plus 4. This will be 16, and the midpoint is 8. Again, I will compute f of 4 multiply by f of 8. If it is less than or greater than 0, I will do these steps. This is the first one, the first condition. Second condition, if I evaluate the function, if f of xi or xl multiplied by f of xr, and this is positive, I find that this is positive. That means the roots now will be located at the upper limit, not at the lower limit. So this is 12. If I find that f of x for the lower limit multiplied by f at the midpoint is greater than 0, so if this is positive, the evaluation here, that means the root is not located here. So I will use this interval only. So in this case, I will set the lower limit x of l equal x of r. The third condition, if x of l or the function at the lower limit multiplied by the function evaluating the function at the midpoint is equal 0, so in this case I will terminate because x of r is the root itself by itself. If this is equal 0, so I will stop here because this is the root that I am looking for. This is the root. Okay, so this method, one of the samples method that we use, we can use this one to solve the problem that we have. If we get this, for example, here, or for example, we start from 4 to 20, so we try to have different step size to compute the roots using. Any question here, ya shabab, for bisection method? This sample method, very sample, very sample, and we want to try this one more and more. Practice this one. We will have more examples, inshallah. This method, what we do. Okay, so we try to reduce the interval step by step or half by half until we get the solution of this one. Let's take this example what we have before. what we did before, we find this one. If we start, because when we check this one, as we said, when we check the table here, we do the table, we find that we have the roads located between 12 and 16. We might start from this initial guess. To initial guess here in this example. So here I have the lower limit is 12 and the upper limit is 60. The first step, what we do, I will compute x of r, or the midpoint. So I will take 12 plus 16 over 2, this will equal 40. Okay. So now, after that, I will evaluate the function the next step. I have f of 12 multiplied by f of 14, and this is positive value. So let's take this algorithm here. This is 16, 12, 16. I have the midpoint at 14. Okay. If I evaluate the function at 12 multiplied by the function at 14, this is positive. That means the ball is not located here. Okay, so the ball will located at this point now. So you can see this becomes the same, will still the same upper limit, but now the lower limit I will replace it by what we call this the midpoint, because I don't want this one. So the lower limit here I will replace it by this point. So here when I evaluated the lower limit for the second iteration, I will replace it by the midpoint. Again, now I have this is the lower limit for the second iteration, and this is the upper limit. I will take 14 plus 16 over 2. This will be 15. I will evaluate the function at the lower limit. The new lower limit will be 14 multiplied by the new midpoint will be 15, and this will be minus 0.6. Here we have this is 15 for the second iteration. So now, because I have change in sign here, you can see I have change in sign in this period. So I will consider only this period from 15 to 14. Okay, no need for this interval. So that means I will replace now the upper limit by XR. You can see I replace the upper limit by XR. Okay, so we will continue like this one. So now I have 14 and 15. We determine the midpoint will be 14.5. After that, I will evaluate the function at the midpoint and what we have it here, 14. Okay, or the lower limit, and we check the value. Okay, if it is positive, for example, in this case it is positive, so in this case I will replace the lower limit by XR. We'll continue like this one. How many iteration we have depended on the error that we want. Okay, so for example, the true value that we want, the true value of this road is 14.8011. So we'll do our estimation until we stop at certain criteria. Where we stop, we determine this one, inshallah, next lecture. Okay, so this the midpoint, you can see it goes closer to the true value that we have. But if we remember, yes, but when we do, for example, the graphical method, we approximate this to be 14.5. 0.75. Okay, while the true value is this point. Any question, Shabab? Inshallah, next class, inshallah, tomorrow we will have more examples about this method. We'll try to solve more problems, and we'll study open methods. Open methods, inshallah, that's usually we started from one or more initial guess, not two. Okay, otherwise we start from one guess or more. Okay, so, and usually the open method will be more efficient than this method that we studied today. any question يا شباب؟
very clear. الله يجزاك خير يا دكتور.